This is a sketch of a DC motor or direct current motor. Let's start with the sketch on the left. The direct current motor has two fundamental components. One is the stator, and I'm going to indicate it in here with this arrow. This is the stator. Then we have the rotor, and it is this part of the sketch here. This is the rotor. But I have also indicated other components which are also fundamental for the DC motor. We have the brushes. This is a brush, and then we have the second brush here. And these two together are part of the stator. So the brushes are part of the stator. So when the rotor starts to move, the brushes create friction between the stator and the rotor. They are fundamental because they transfer the energy from the stator to the rotor. And the other fundamental components which allow the rotor to move are the coils, which are drawn in here. Let me circle in red the coils. And some of them you can see that are different from the others. So, for example, this one here has a dot inside the circle. That means that the charges inside the coil are moving outwards of the coil. So they are moving outwards, and then they are going to be connected with this other part of the coil which has a cross inside. And that means that the charges are entering the coil. So you have to imagine that these dots here are linked, are connected to the crosses. So for example, this one here is connected to this, and so on and so forth. So we have some kind of solenoid. All these coils are connected together in such a way that the field is amplified. And we can use the right-hand rule in order to understand where the flux is located, and I'm going to say more about this. In the stator, we can see that we have some voltage here. There are also some coils on the stator, and these coils are necessary to create the flux which goes in this direction, like this arrow here, this red arrow, and this flux will be fundamental in order to create a current inside the coils. VE is the voltage of excitation. It is related to the excitation circuit. We will analyze it more in detail. Mathematically, in order for the motor to work, we also need to have this voltage here, VA, which is the voltage that occurs between the brushes. If we take a cross-section of the motor, in particular this section here that I have highlighted in red, section AA, we have the sketch on the right. We see the brushes here. Then we have one of the coils that I am highlighting now in red, and then we see the flux, the magnetic flux passing through the coil, and also the voltage, of course. The flux and the current are going to create a force acting on the sides of the coil. Let me mention one more time that this coil here is rotating with the rotor, whereas the brushes and the voltage VA are related to the stator, so they are stationary, but this coil can rotate with the rotor. So these 2 points here that I am highlighting in red is where the rotor is going to rub against the brushes, so there is friction. The disadvantage of having brushes is related to the fact that these brushes are going to be worn out after a certain period of time, so you have to change them. If we take a look at the coil here, this coil will create some angle that I will call theta with respect to this vertical line, for example. This is the coil here, and let's assume that the length of this coil is h, which is the distance from the two endpoints. Due to Ampere's theorem, we know that at the endpoints of the coil there is a force acting like this. Why is that? Well, because the magnetic field is directed like this. This is the same field that we have in here, drawn in red. Then we have the current generated in the coil, and on the sides of the coil, here and here, on one side the charges are moving down, and on the other side the charges are moving up. So the right-hand rule is going to give us two forces directed like this. One like this, and the other one like this, for example, or vice versa. In this case, I'm assuming that the charges are moving down here and up in here. That's due to the right-hand rule. The force according to Ampere theorem, is equal to the current that I will call I sub A. This subscript is related to this one here. It is called A because it is related to the armature circuit that I'm going to discuss more in detail next time. But it is a current, the current inside this coil. Then we have the length L of the two sides of the coil. So for example, if I draw the coil, I can see it like this. This length here is L, this is L, then we have H. So I'm thinking of the coil as a rectangle for the sake of simplicity. And then we have to multiply by the field that I'm going to call B sub E, which is this one here and also this one here. You can see that these two forces create a torque, and I'm going to call it C sub C. The letter C here is related to the fact that in Italian we give torque a different name, which is coppia, and you can translate it as couple, for example, but that's not really the right translation. The right translation would be torque, and this other subscript here, this letter C, has nothing to do with torque. It has to do with coil. So this is the torque of a single coil. The torque of a single coil is the force, F, multiplied by the distance between the two directions of the forces. So the distance would be this one here that I am highlighting in blue, and that would be H times the sine of the angle theta. So if we use the formula for the force, we have Cc equal to Ia Be LH sine theta. LH is the area of the single coil, so I can call it A, for example. We have Ia Be A sine theta, and now I'm going to call the product between the area of the coil and the magnetic field, I'm going to call it phi sub E, which is the flux. This is also called the excitation flux, and it is still related to these vectors here. It is related to the magnetic field, but we also have to take into consideration the area of the coil, because the larger the area of the coil, the greater the flux. So this is an important parameter. The flux is one of the most important elements that we have in the motor. Now, if we want a total torque, C, we have to sum all these torques that we have on the single coils. And this is not something very trivial, because for a real motor, the geometry of the rotor is going to affect the calculation, and it can be different from motor to motor. So I'm going to make an approximation first in order to let you understand the gist of the story without getting into too many sophisticated details, of course. So now I'm going to make a simple approximation. I'm going to approximate it like this. I'm going to integrate the single torques, C sub C, by assuming that the coils are infinite and they are continuously distributed. So I'm integrating Cc over the infinitesimal number Nr, where Nr is the total number of coils that we have in the rotor. dNr is the infinitesimal amount of coils that we have over an infinitesimal angle. So dNr is equal to the total number of coils multiplied by d theta divided by the total angle, and the total angle in this case is just pi, if you think about it, because if we go back to the sketch of the motor, this is the single coil. Let me do it like this. This is the center of the rotor. When we rotate this green line over an angle equal to pi, you can see that this side is going to span across all these coils over all this region, whereas this other point here is going to span over all these regions. So we have to integrate over pi. That's why I'm going to divide by pi here, because we integrate from 0 to pi Cc times Nr d theta over pi. So this Nr here is just a constant, it is the total number of coils. And then we just have to substitute the expression for Cc. So we have integral from 0 to pi of sine theta d theta, and then out of the integral we can put Nr over pi times Ia times phi sub E. Now if we integrate sine theta d theta over pi, we just get 2. So we have 2nr over pi Ia phi sub E. And this is a very general result if we replace this constant here with another one that I can call K sub C. This is also called the constant of the motor related to the torque. This is just a constant of the motor related to the torque, which depends on geometry. So if we have a different geometry, we still get a very similar result. The only exception is that this constant will be different. It will have a different value. It will not be like that. So this is just an approximation, but in any case, For every DC motor, we can write down the formula like this: K sub C times I sub A times phi sub E, where I sub A is the current in the armature, phi sub E is the excitation flux. And I will say more about this, of course. We still have to understand more in detail what I sub A is and also phi sub E is. Then, according to the Neumann-Faraday length law, we know that in the motor, since we have a flux going through some coils, we have an electromotive voltage that I will call E sub C, which is equal to the derivative of the flux, d phi C dt. So this will be d over dt of, we know the expression for phi sub C, which is v sub E A times sine theta, and this is equal to v sub E A times theta dot times cosine theta. Theta dot is also called omega, and this is the angular velocity of the rotor. So it is the angular velocity of the rotor, and we can rewrite this as phi sub E times omega cosine theta. And this is the electromotive force that we have in a single coil. If we want the total electromotive force, we have to integrate in a very similar manner E sub C d and r. So I'm going to make the same approximation, of course. And in this case, we have to integrate E sub C n r d theta over pi. Now we have to be careful here because E sub C contains a cosine here, not a sine anymore. So we have to integrate over an interval such that the cosine is positive, because all these voltages should contribute in the same manner with the same sign. So there is not a voltage that's going to oppose with a negative sign, so we still have to consider a positive sign. We have to integrate from minus pi over 2 to pi over 2, for example, because in this interval the cosine is positive. So we have phi sub E omega cosine theta nr over pi d theta. And therefore here we get 2 nr over pi phi sub E omega. This is still equal to the constant that we have above, K sub C, but if we want to be more general when the geometry is different, this result here would be different. This would be a different constant that we will call K sub E. So the result that we have here is K sub E, phi sub E, omega for the electromotive force, the total electromotive force. And we also have that the total torque C is equal to K sub C, phi sub E, I sub A. K sub C and K sub E are constants of the motor. They depend on the geometry, on the coils, on the geometry of the rotor, but they are constants once we have the motor. And we will move on from here next time.